This is a work through for question 6.1 in the workbook, parts D and E, so the final part of this question. If you're watching this video before parts A, B and C, stop it and go back and watch the first part, because this question is sort of a chaining style question, so it's been leading up to this point. Right, it's been a bit confused about 6.1D. It really is just an exercise in looking very carefully at the units, and all the information is quite clear in the question. There's a little bit of juggling around with units, otherwise we should be able to look at the units and dimensions and get the correct answer in a very small sort of number of steps. So the question states, part D, the real engine has a power of 100 kilowatts and to be running at 2,500 thermodynamic cycles per minute. Obviously you need to get into cycles per second pretty quick. Estimate the required cylinder capacity, and this is the total for all of the cylinders in the engine. We're not told how many cylinders this engine has, so we'll be finding the total volume of all the cylinders. Of the swept volume, V1 minus V2. And then we're given a hint. So find the mass of air to be taken in the cycle using the specific work from part C. So we need to write out what that specific work does, and more importantly the units. And it says consider the air in state 1 to occupy the volume V1 minus V2 when the unit valve shuts. All this statement is really saying is that we're not going to be adding on any extra volume to our final answer. Okay, we're just making an assumption that V1 minus V2 is the total sort of stroke length of the cylinder. Okay, so the first thing we're going to do is we're going to write out all the information we're given in this part of the question and pull back in that value from the solution to part C. Right, okay, these are the variables we're given. Obviously there's 2,500 cycles per minute, we need to put into cycles per second. Okay, and again this is where understanding the dimensions of certain properties are really helpful. So we're given the power. Okay, power is a rate function, it's the rate of work done or the rate of energy. So this is in basically kilojoules per second. Okay, we've got cycles per second. So you can see now that we can get to the amount of energy per cycle in terms of kilojoules. Okay. So now the energy per cycle equals 2.4 kilojoules. Just divided power by this value here. And you notice that the net work done is in kilojoules per kilogram. Okay, and we've got energy here per cycle. So now we can quite quickly work out the mass of air in kilograms per thermodynamic cycle. Okay, so that mass equals 2.4 kilojoules divided by this 1187 kilojoules per kilogram. Okay, just take care obviously which way you divide through. It should be fairly obvious. If you invert this you're going to get an enormous value, 400 kilograms of air, which is obviously not very realistic. So you can always sort of crudely check your answer just by looking at the magnitude of what you get. Okay, so that's our final answer. 0.002 kilograms of air per cycle. Okay, so now we've found the mass of air. The next stage is to look at calculating the volume, and this is really quite simple. Right, this is all we need. We know the pressure and temperature at state 1. So we can put in pressure of 1 bar. We know the mass, 0.002 kilograms. R is 287, and the temperature, going back, is 288 degrees Kelvin. So we can rearrange to find the volume. And that's the answer that it should have in the book. 1.67 times 10 to the minus 3 meters cubed. Okay, that's the end of part D, and then the final part of the question, part E. Right, part E is just the final part. This is actually quite a good sort of graphical illustration of the comparison between the Carnot efficiency of an engine and the real efficiency. So first of all, I'll ask you to work out the Carnot efficiency, or theoretical efficiency, of our engine. And this formula is one that you really should commit to memory. Okay, in last year's exam, so in 2012-13 examination, there was an entire question based on theoretical efficiency of 3 different types of thermodynamic cycle. Okay, so filling in the numbers, T cold is 288, TH was 3,400 and something, 3454. Remember, always in Kelvin. If you do this in Celsius, you'll get completely the wrong answer. 0.916 is what you should be getting. Okay, we're just plugging 2 numbers into a very simple formula. Right, the final part, the question E, 6.1E, asks you to sketch on the theoretical maximum efficiency cycle onto the TS diagram. So I'll quickly redraw that. Right, that was the cycle we started off in part A when we drew it out. Remember, process 1 to 2 and 3 to 4 are reversible or diabatic or isentropic. And then we have 2 isochoric processes, constant volume. Okay, the Carnot efficiency is super easy to plot in temperature entropy space. Again, we know that it is 2 reversible or diabatic processes and 2 isothermal processes. And you can see that we've got temperature and entropy. So all we simply do is take the minimum and maximum temperatures and draw a square. Okay, so you can see that the red square is our Carnot efficiency of our engine. So our actual efficiency, or work done, is just in here. Work done under the Carnot cycle is the entire red square. So you can see that all of that red shaded area is lost in our real engine. Again, a rough rule of thumb is most real engines, real thermodynamic cycles, are approximately half as efficient as the Carnot cycle. Okay, and looking at that, it seems about right. You know, sort of about half, sometimes a bit more, sometimes a bit less. It depends on the type of cycle and the processes involved. But you can see that this is now all of the theoretical energy that we can't harness. Okay, so that's the end of question 6.1. Again, it's a very nice sort of type of question. It sets you through, and it's really good for your revision. So, like I say, it's a really good one to have attempted to solve.